Okay, so welcome to today's GOAT seminar, and our speaker is Legerský, who will tell us something about flexibility and NAC-colorings and stable cuts. So,
thank you. You see, I will speak about three topics that somehow link to each other. Probably you have some idea what I mean by flexibility. So by flexibility, I will mean something like this. So you will have also a chance to play a bit. I will pass it around in a moment. Maybe some of you have heard about NAC-colorings, but don't worry if you haven't. It's not something that will be common in graph theory. So those are some special edge colorings that I will introduce. And by stable cuts, I mean independent vertex cuts. So I just call them for short stable cuts. And this is a joint work with Katie Clinch, Daniel Garamfolgi, John Hasselgrave, Tony Huing, and other Tony, who likes to be written as Anthony, but he's called Tony usually. Okay, so what I mean by something flexible, I have a graph and I fix its edge lengths and I ask whether it can be deformed or not. So here you can imagine that I have a graph whose vertices are the joints and the edges are the links, and you can see that it can move, so it's flexible, so the edge lengths are preserved. So this is what you should keep in mind when I speak about something flexible. There is one thing hidden slightly in that one. There is a triangle that is degenerated into three collinear points, so there's some, you can see there's a non-visible edge, but there's a graph behind. So this example is known for a rather long time. So in 19, Dixon gave a construction of this complete bipartite graph K33 that is flexible. If you would, I don't have an example that would be like 3D printed, but if you would have a 3D printed example of this one, and you would switch one of the links to something that is slightly shorter or slightly bigger, it would stop moving. So this is like very special situation in which it can move. And so this is like you have two orthogonal lines, and you put the vertices on these two orthogonal lines, and then you place the edges to get the complete bipartite graph. This is coming from K44, so the complete bipartite graph on 4 and 4 vertices. You forget some of the vertices, or you take the symmetric realization, you forget some of the vertices, and you get another flexible realization of K33. So he gave some constructions, and more than 100 years ago, it was proven that actually for K33, you don't get any other flexibility than just these two, like two orthogonal lines and something that is dihedral symmetric coming from K44. So this is just to introduce a bit what we sometimes call, if it got broken, either fix it or just I pass from the other corner.
That's why it was flexible.
This is what we sometimes call paradoxical flexibility. So if you change the edge lengths, you can have something rigid, but for some very specific choice of edge length of the positions, you get something flexible. So maybe let's start with some simpler graphs. So if now I take just the 4 cycle, I think everybody can imagine how this 4 cycle flexes in the plane. So if I keep the edge lengths fixed, I can take almost any realization of this 4 cycle and it will be flexible. So I would have to do like something very special to get something that cannot move. Namely, if you just stretch the 3 edges and you put the 4th one as the sum of the 3, then it's not flexible, but that's like a very special situation when it cannot flex. For the graph on the right, if you have a triangle, then the positions of the vertices are given by the edge length. If I add another triangle, again, it's fixed. Having these two fixed, again, knowing this distance and this distance, this vertex again has a fixed position. So for almost any realization, this will be rigid compared to the one on the left. If I take this graph, now it's not so easy to see that this would be generically rigid. Namely, it would be rigid for almost all realizations. We will see a theorem that would prove that this, for almost any realization, it's rigid. Yeah, I'm walking too much there and back, sorry. But there is a very special one. If I now keep the same graph, it's called the 3-prism graph, and now I take these 3 edges to be the same length, and I take the triangles to be the same, then it can rotate like this around. So for something very specific, I can get a flexible realization. Okay, this is somehow pictorial. These are like pictorial concepts in rigidity theory. Let's put it a bit on firm ground, so I give you some brief definition. But keep in mind, just like these pictures, those linkages. If I speak about something rigid, I have something more. This is not in the plane, but in 3D, this is rigid framework. Please don't try too hard because it's. I think it's reasonably solid, but not. Okay, so I have a graph, so I denote my vertexes by VG and my edges by EG. And now what I mean by a realization is a map from the vertex set, let's say, to the plane. Of course, you can do it in R3, like for this one, or we will briefly mention spherical linkages or spherical realizations later during the talk. But for now, everything is in the plane. And I will be mostly speaking about finite graphs, so this is here just because there are some results in infinite graphs as well. And the only thing I require is that you map the vertices in a way that no edge degenerates into a single point. So if vertices are not adjacent, then they can be mapped to the same point, but not if they are connected by an edge. So this is realization. And now by a flex, I mean continuous, I can even say, let's say, parametrization of realization such that the edge lengths are preserved. So like if you move that gray example, what you do is that you somehow follow a flex of this graph. So the edge lengths are preserved. And of course, there are some trivial flexes. So if I take the whole graph, the whole framework, and I move it somewhere without deforming it, that's somehow trivial. It's coming just from rigid body motion. So I want to throw away those trivial ones. If like all the distances between vertices, between pairs of vertices are fixed, then it means that I'm just moving everything. So that's not interesting. I want to deform it somehow. So I want some non-edge to change its distance, so you can really see that there is some deformation. Yeah, okay, so I call a framework flexible if it has a non-trivial flex, so I can deform it while preserving the edge lengths. And otherwise, I would call it rigid. So the gray ones are flexible frameworks. The metal one is a rigid framework in R3. So Sachs proved that it's simply hard to decide whether a given framework is rigid. So that's not such a good news. What is a good news for rigidity theorists is that if you now look not at a framework, so framework is a graph together with a realization. Now I want to look only at graphs. And one can prove that fixing a graph, either almost everything, like almost all its realization will be rigid, or almost all will be flexible. So I can speak about generically flexible graph, like 4-cycle, or generically rigid graph, like the triangles we've seen, that for almost all realizations, I would have something. I get a rigid realization. So I can somehow forget about the realizations, and assuming that the coordinates or the edge lengths are generic enough, I can just look at the graph that it's rigid or flexible. Does this make sense? Because this yields some strange statements like minimally rigid graph with a flexible realization. So we have to somehow distinguish that we can look at generic behavior that can be done on the graph level, but then we can also ask whether for this generic behavior I have the opposite behavior, like would be if I return back here. So this graph is generically rigid. So for almost all realizations, I get something rigid, but doing something very specific, like choosing this particular one, I get something that is flexible. So it can happen that the behavior is different than the generic one, but you have to do some very special choice of edge length or of a realization.
Maybe I have a question. So we were talking about graph, not about also its length, in a way that in general I can just consider a graph. And can I? So if I map the graph to the plane, it can be rigid. But if I map it different way, it can be flexible.
Yes, this can happen. But if you fix a graph, for almost all, you will get the same behavior. So for some measure 0, you will get the other behavior. That's the crucial point. That
it's also okay to assume that like I place the points randomly in the plane and then like.
Yeah. If you do it randomly, then you know that it will be always flexible, or
you always measure.
Yeah. I don't. So you can imagine that, for instance, you take all the coordinates to be algebraically independent, and then you know that for algebraically independent coordinates, the behavior will be always the same once you fix the graph. Okay, but this basically means that on a certain level, I can talk only about graphs. Maybe one more concept: graph is minimally rigid if removing any edge gives me something that is flexible. So that's somehow natural class of graphs to look at. Those that they have the least number of edges that is necessary to be flexible, and they have them distributed in good way so that they are. So sorry, that the least number of edges that is necessary to be rigid, and the edges are distributed in a way that they are indeed rigid. And now looking at this generic behavior, Polacek-Geiringer proved in the 30s, and it was rediscovered by Laman in the 70s, that a graph is minimally rigid. So I'm looking only at the graph, so I'm looking at the generic behavior, if and only if certain conditions are satisfied. So the first condition is that the number of edges of the whole graph is twice the number of vertices minus 3, which is maybe a number I want to write on the blackboard, because in rigid theory a magic number. So I have twice the number of vertices minus 3 is the number of edges. If you think a bit, this is not so surprising, because like every edge gives me one constraint, and I have b vertices. I'm in the plane, so I have x and y coordinate for each vertex. So I have 2 times b number of coordinates. If now I want to determine what's going on, and I have 3 degrees of freedom of rigid body motions in the plane. I can rotate around the origin, that's 1, and I can translate along the x-axis and y-axis. So that's other 2. So I have to subtract these 3 degrees of freedom. So this is the number of edges I need to make it rigid. And the other condition somehow tells me that I don't have too many edges in one place, because then I would be lacking edges in some other place of the graph. So they have to be distributed nicely. In general, in d-dimensional space, this is a necessary condition, not sufficient, but in the 2D, we know that it's also a sufficient condition. And although the condition is somehow ugly in the sense that it's for all subgraphs, there are public algorithms that can check this in polynomial time. So general rigidity can be checked in polynomial time. Okay. So now, again, back to the paradoxical motion. So I have a rigid graph or a minimally rigid graph, and now I ask whether I can do something very special and get something flexible. So this is something that we proved during my PhD using the concept of NAC-colourings. So NAC-colourings are edge colorings by red and blue, but please forget what you know from graph theory about edge colorings. So this would be too little colors to color in the graph theoretical sense the graphs. What I care about is that I use, of course, both colors. And now for every cycle, either everything is blue or everything is red, or I have at least 2 red and 2 blue edges. So if you look at this graph, I don't know whether the colors are visible. Well, this would be a NAC-coloring. This is not a NAC-coloring, because here I have blue, 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 and just a single red edge. So here I have something that we call an almost cycle. So the NAC is for no almost cycle coloring. Okay, so the left one has to check all the 4 cycles and 3 cycles. Those are obviously monochromatic. To see that this is indeed a NAC-coloring. The right one is not, because of the cycle I was showing. And now the main theorem about NAC-colorings is that now if I fix a graph, there exists a flexible realization if and only if the graph has a NAC-coloring. So the main motivation was to study the rigid graphs, whether they have a flexible realization or not, but the theorem somehow doesn't require to assume a rigid graph, but obviously for graphs that are flexible, namely almost all realizations are flexible, that's somewhat trivial that they have a flexible framework, but this tells me how I can check for a rigid graph or minimally rigid graph whether it might have such a special realization that is flexible. So for instance, for this graph, I can check whether there is a NAC-coloring or not, so I can start coloring. So let's put this edge red. And of course, if I have a 3 cycle, there is not enough edges to have at least 2 red and 2 blue, so 3 cycles are monochromatic. So I continue and I color all of these red. And now I have to choose for this triangle blue, because if I choose it red, then everything would be red. So I make it red. And now looking at this 4 cycle, I already have 2 red edges. I have 1 blue, so this one has to be blue. But now I have a problem, because if I look at the outer cycle, I already have 2 red edges, so I would need second blue. But for instance, here I already have 2 blue and just 1 red, so I would need second red. So there is no chance how to construct a NAC coloring for this graph. So this is a small graph, so it's easy to check, but in general, checking whether a graph has a NAC coloring is NP complete. So what we try to do is to look at some special class, namely to look at minimally rigid graphs. So now the least number of edges that is necessary to be rigid, so graphs that have this property, whether they admit flexibilization or not. And it's basically from based on the previous example, it's easy to see that if you have a 2-3, it has no NAC coloring. Does everybody know what I mean by 2-3? I start with an edge, and now I do degree 2 vertices that I connected to an edge. So in general, I pick a graph, which is a 2-3, I pick an edge, and I add a new vertex that is adjacent to these vertices. And because I'm basically just adding triangles, there is no chance to have a NAC coloring, because triangles are monochromatic, and like the 2 new edges, they have to keep the color of the previous one, so I cannot find a NAC coloring. So this is easy observation. What I conjectured in my thesis was that looking at the minimally rigid graphs, also the converse is true. So if I now pick a minimally rigid graph that is not a 2-3, then it has a NAC coloring. And in the thesis, I was not able to prove it, and then I asked some of the people who are listed whether we could prove that, and we struggled quite a lot. And eventually, after asking more people, Daniel came with the result that basically solved the conjecture almost immediately. So, so the result is about stable cuts. I will show the result in a moment. But before that, I would like to link stable cuts and NAC-colourings. So by stable cut, again, I mean a set of vertices such that there are no edges between them. So it's stable or independent set of vertices, and it's a cut. So if I remove those vertices, I get a disconnected graph. And now if a graph has a stable cut, it has a NAC-coloring. That's quite easy to see. Basically, if you separate the graph by removing the vertices, you got everything on the left blue and everything on the right red, and because it's independent, you don't get any almost cycles. So we did know this ingredient. What we didn't know for a long time was this result, and one I will show in a moment, how it is with graphs with few edges, whether they have stable cuts or not. So Chen and Yu proved that they called it fragile graphs if there exists a stable cut. So that if a graph has at most this number of edges, then there is always a stable cut. This is not the case that we could use in the minimally rigid case, because in the minimally rigid case we have -3 here, the -4, but it's just one off. And actually, one can also see that this is the best you can get if you have this number of edges. There are graphs that do not have stable cuts. For instance, the free prism that we saw. Luckily, Le and Pfender improved the result by going to graphs that have 2v-3 edges, and they show that either graph with this number of edges has a stable cut, or it belongs to a special class of graphs that is nicely described, namely an edge, triangle, and free prism are in this class. And now the operations they do is that they pick 2 graphs in this class and they glue these 2 graphs along an edge. That's one option, or you pick a tree cycle in both graphs and you glue the two graphs on this tree cycle. So by doing these operations, you do get all the graphs that do not have stable cuts and have this number of edges. And this is such a nice description that it's easy to just now check that for this class, if it's not a 2-3, you have a NAC-coloring because you have these 3 prisms and they have NAC-colorings. So just by doing them, you can extend the NAC-colorings easily. So stable cuts solved our problem in rigidity theory. So we were thinking, okay, can we use some more rigidity theory to prove something more about stable cuts or about existence of stable cut? So now let's jump for a moment into realizations in the sphere. And the only thing I need is basically looking at generic behavior. Whether you look at the rigidity in the plane or in the sphere is the same thing. So graph is generically rigid in the plane if and only if it is generically rigid on the sphere. So we have the same class of graphs. They are a bit more difficult to produce, like the spherical ones, but one can also produce some spherical linkages. So that's one ingredient we need. The other ingredient is that we proved that connected graph has a spherical flexible realization if and only if, and we did it using some colorings, but I don't want to introduce the definition of the colorings. Basically, the if and only if was if it has a stable cut. So now, just putting these two things together, just taking the reformulating this one, a graph is flexible in the sphere if and only if it is flexible in the plane if and only if it is flexible on the sphere. So if I have a flexible graph, I have a flexible realization on sphere, so I have a stable cut. So every flexible graph has a stable cut. So that's how to prove, or we can prove this just by picking some results from rigidity theory. What we didn't like about this one is that to prove this theorem, this was again aimed at the non-generic behavior on the rigid graphs on sphere. So it requires some heavy algebraic geometric machinery to prove this. While this is rather combinatorial statement, we have flexible graphs, we do no combinatorial description of those, so we would like to prove that they have stable cuts. So we were able to prove this directly combinatorially, avoiding this algebraic geometric proof for the sphere. So here I again put the theorem by Chen and Yu just to show you or to convince you that what we prove by saying that flexible graph has a stable cut is a generalization of this statement. So a bit more precisely, what they proved was that if you have a two connected graph with at most 2 v minus 4 edges, then it has a stable cut that avoids a given vertex. So the one connected case is kind of trivial because if it's just one connected, not two connected, the vertex that disconnects the graph is a stable cut on its own. And you cannot avoid that one in many cases. So it makes sense to look at the two connected case. And what we can prove that if I now have a two connected flexible graph, then again I can find a stable cut that avoids a given vertex. So that generalizes the class because here if I have only 2v minus 4 edges, it's less than this number. So every graph that has 2v minus 4 is flexible, but there are many graphs that have more edges and they are still flexible. So this gives a sufficient condition of the existence of a stable cut. And we can actually prove a bit more. You can pick two vertices in your graph and ask whether there exists a stable cut that would separate these two vertices. So what you have to do is that you pick these two vertices such that they are not in the same rigid component, and rigid component is a maximal rigid subgraph. So you have a flexible graph, so if you look at flexibilization, there are some moving parts, and you need to pick vertices that are like in different moving parts, if I say vaguely. And so the moving parts are separated by a stable cut. Moreover, I know that for the stable cut, it uses at most one vertex from each of these moving parts of this rigid component. So this is a generalization of the theorem by Chen and Liu. Yeah, and we provide an algorithm how to find such a stable cut, so it can be done in the cubic time with the number of vertices. So that was the relation with stable cuts, and another topic we focused on was to count the number of NAC-colorings made for some specific graphs or to give some bounds. So the first thing we do is, because you can just swap red and blue, if we count NAC-colorings, we decided to count them divided by 2 because swapping the colors doesn't really change the NAC-coloring. So by this number of NAC-colorings of G, I mean modulo swapping colors, so I divide by 2. And very easy observation, if you have something that is not too connected, you can decompose your graph into blocks, so maximal 2 connected subgraphs, and because they are connected just by a single vertex, there's like not really, there's no cycle that would go from one block to the other block. So basically, you can just look at the NAC-colorings of the individual blocks, and then you combine them together to get all NAC-colorings of the whole graph. And this gives you just a formula. Just to mention that, like, you can look at 2 connected graphs when you count NAC-colorings. And we can prove the following bound. So if I have a graph on n vertices, then I have at least this number of NAC-colorings. So it's like roughly 4 to the n, where n is the number of vertices, is an upper bound on the number of NAC-colorings. So what I would like to present now is to look at 3 natural, from rigidity point of view, natural classes, how tight this bound could be. So I look at flexible graphs, minimally rigid graphs, and rigid graphs, and just some bounds what we can do for these 3 classes. So if I have a 2 connected flexible graph, I can count these rigid components, this maximal rigid subgraphs that would stay rigid. If I have flexibilization, they move with respect to each other. And now for every flexible 2 connected graph, the number of NAC-coloring is bounded from below by 3 and the logarithm of the number of these rigid components. And definitely you can find graphs that have much more than this number. If you take just a path, then the number of NAC-coloring is something like 2 to the n minus 1 or 2, depending who you count, but because you can just pick any coloring by red and blue minus those that are monochromatic. So this is a general lower bound for flexible graphs. For minimally rigid graphs, we tried to construct a class of graphs whose number of NAC-colorings grows as fast as possible. And what we can achieve is taking this graph and just like continuing the sequence here. We get a graph with even number of vertices. One could do some small trick to get also the odd numbers, but let's state it just for even integers. So this is a minimally rigid graph for every number of vertices, and the number of NAC-colorings is at least square root of 2 to the power of n. We cannot count exactly for this one. My hope was that we could give just a precise formula, but it was we failed to really give precise answer here. Just to compare with the upper bound we have, here I have square root of 2 to the power of n, while the upper bound we know is 4 to the n. I put here also this number because this is just the 2 to the number of edges of a minimally rigid graph. Okay, there could be minus 1 in the exponent here because I divide by 2. So this is just to convince you that the upper bound we have, the general one, is better than the naive one for minimally rigid graphs. But yeah, I mean, they are pretty far from each other. This square root of 2 to the power of n, 4 to the n is quite a big gap. So this is minimally rigid graphs, and in the class of rigid graphs, so they have more edges than in the minimal case. We looked at the complete bipartite graphs on N1 and N2 vertices, and there we can compute exactly. They have this number of NAC-colorings, which is still much less than the general bound, because the number of vertices here is N1 plus N2, so I have 2 to the N, but the general bound is 4 to the N, so there's still a gap. Yeah, so that's what we have done so far. Maybe let me briefly mention what we would like to do, though we have some doubts in some cases. So we have a conjecture how it is for the unique NAC-colorings, and now by unique I mean modulo swapping colors of the minimally rigid graphs. I will not tell you the conjecture, but we hope we could do something in this direction, so to really classify all minimally rigid graphs with exactly one NAC-coloring modulo swapping the colors. Bit more ambitious thing would be to look at the graphs that have one edge more than the minimally rigid case. This would contain so-called rigidity circuits. Those are somehow interesting for rigid theory. We do hope that for NAC-colorings maybe we can do something in this case. For classifying graphs that have stable cuts and this number of edges, I think that's too hard. It would be nice, but I don't think we can really describe all graphs that do not have or do have stable cuts on this number of edges. Maybe what I would like to mention here is if you take the question whether a graph has a stable cut, that's NP complete for graphs that have maximum degree 5. And even if you take a graph that have 2 plus epsilon times the number of vertices, so if the number of edges is at most this for some fixed epsilon, it's still NP complete to check whether a graph has a stable cut. So that there's some small gap in between, like for 2n minus 3 or like 2v minus 3, we know that it's polynomial. Here we know that it's NP complete, so -2, -1, -0, or some fixed plus constant is somehow what is not known in between. And there's also some ongoing work with Petr Laštovička in VLED. So now we are finishing a proof that similarly as for the stable cuts, the existence of a NAC-coloring is NP complete for graphs with maximum degree 5, and also if you restrict to the 2 plus epsilon times the number of vertices. And Petr has implemented some ideas how to improve the algorithm for searching all NAC-colorings or checking the existence. Of course, this algorithm is still exponential, but it's much faster than my naive implementation that I did some years ago. And he implements the algorithm in terms of the package PyRigi. So I'd like to make a small commercial. So we are developing a package for rigid and flexibility of graphs or Bayesian frameworks. So if you want to have a look, search for PyRigi. And I fear you have to write PyRigi package because Google, for some reason, if you write just PyRigi, it thinks it's Pirgi, which is some village in Italy, and you get just results about that one. But if you write rigidity theory PyRigi, you should get to the package. Okay, that's all. Thank you.
Okay, any questions? Okay, so can you say something about, let's say, the topological properties of this flexibility, of this space of flexion, let's say?
So
in the minimal rigid case, I would assume they are like one-dimensional or something.
So generically, in the minimal rigid case, it's 0 dimensional. You have just like finitely many isolated solutions. if you look at something that is parametrically flexible, you can so usually get something y-dimensional, but sometimes you can get also higher dimensional objects if you choose. Of course, not for every graph, but for some graphs, we do have examples that you have more degrees of freedom. That's something we are hoping to do with another colleague, to like have some kind of combinatorial conditions, probably not really characterization, like when we can have more degrees of freedom. Regarding like the topology, if you take something that has generically 1 degree of freedom, so you take a minimally rigid one and you remove one edge, then generally you have a curve of realizations. And for this one, Josef Šicho, Odi Boron, and Ayush, I don't remember, that they have a paper that can compute the genus of this curve. So, I mean, they don't have a formula, they have an algorithm, so you can plug in your graph and it outputs the genus of that curve over C. Yeah, many things are much nicer over C than over R. So.
Yeah, definitely.
I mean, I didn't tell you today, but in the NAC-colorings we also go to the C because there we have some tools that we can use. Yeah.
Oh, so it's like a sphere in C.
Yes. Like many of these questions, you look at the polynomial system, and over algebraically closed field, you have many more tools than over R because you can count solutions over C, over R. For a specific system, of course, you can count the solutions, but if you want to look, so given a graph, you can ask how many, minimally rigid graph, you can ask how many realizations this one graph has with the same edge length. So over C, this is a well-defined number. Over R, you can get various things from 0 to the number over C. So I think going to C is a good idea usually. Still using someone that you start with a real problem, like very often we go to C, but we know that, for instance, the edge lengths are real, so maybe we can do some trick that uses the fact that like we started with a real problem, but we are in complex space. So my question would be, if you would have any ideas in these directions, like fixed parameter tractability or something, I would be happy to discuss.
Can you tell us how the energy computation works?
You mean for this max degree 5 or the general one?
The general
one. So it's reduction to 3 subs, and yeah, Daniel just I cannot draw the graphs right now, but it's a nice paper. It is easy to read. You just look at those few pictures he has, and what we yeah, I mean those are some gadgets. Of course, it's not just like. It is not difficult, but it's not something I will be able to do right now. We somehow use this idea to change the gadgets so that we get just max degree 5 in the gadgets. Yeah, I'm happy to show you, but I don't dare to try now to draw the graphs. Maybe I can encourage Peter to give a talk at some point about it.
So that would be the hardness, right? So what about like containment NP? Because it seems to me that from the definition you cannot like verify that given coloring is an NAC-coloring. That was the part that I was like also thinking about.
That's a good question. It's easy to verify because what you can do is I don't have it on the slide. So coloring by red and blue, assuming that I use both colors, is a NAC-coloring. If and only if what I do is I define G red. I keep the vertices of the original graph, and now I take red edges. And I do the same for blue edges. And now I look at the connected components of these two graphs. And it's NAC-coloring if and only if the connected components are induced subgraphs. So this is something you can check out any time. Yeah.
Some more questions? Okay, if not, let's thank the speaker again.